Hello student, the foundation of classical electrodynamics course. So under module 4 we have lecture number 70 today, and we will going to continue our discussion on Maxwell's equation in matter. Today have class number 70. So in the last class we find that when we have a material, when we calculate the Maxwell's Maxwell's equation in a matter, then the source equation, two equation containing the source is modified. One is divergence of D is rho f, free charge density, and that is one modification where D is equal to epsilon 0 E plus polarization P, and another equation that we modified is the curl of H is equal to free current density plus the rate of change of displacement current, where H is defined like B divided by mu 0 minus M. So these are the two equations that we modified, but the other two equations, these are the equation having source term, but the other two equations like divergence of B equal to 0 remain same, and also the equation like curl of E is equal to del B minus of del B del T is also remain intact. There will be no change. Only change when we discuss the Maxwell's equation in matter, then the term associated with the charge density and current, the charge density and the current density we are going to modify. This is the Maxwell's equations. In the matter. Well, let us try to find out what should be the boundary condition then. So the boundary condition for this set of equation. Boundary condition. So now I write the Maxwell's equation in integral form. These Maxwell's equation in matter in integral form if I write. So I should have the first equation in this way. This is the integral form. So I should have, since this is integral form, I should not have this operator anymore. So I have the closed surface integral of d dot ds is equal to the total charge, free charge. That is first one. Second one is the magnetic flux is simply 0, that is the consequence of the second equation. Then we have the Faraday's law, and if I write in integral form it should be E dot dl is equal to minus of d dt, and then we have the magnetic flux B dot ds over surface integral, and finally we have the closed line integral of H dot dl, that is the free current, and then plus del t of the integration of d dot ds. So quickly, if I understand in the right hand side, so this is corresponds to the equation divergence of d equal to rho f. This is the equation corresponds to divergence of B equal to 0. This equation corresponds to curl of E is equal to minus of del V del T, and finally this equation is curl of H is free current density plus del D del T. So these are the equations. Left hand side we have integral form and right hand side we have the differential form. The usual form is the differential form, but you should also appreciate the integral form, and in this case for boundary condition we require this integral form. So let us now do what is the boundary condition. So we have, like before, we have a surface like this, this is the surface we are having, and try to find out the boundary condition for D. So we had a surface pillbox like this, below that we have the dotted line. So the surface is over this region, and let us consider sigma f to be the free surface charge density here. And if I have 2D, so this is the region 1, so let me consider this as region 1. Say here we have region 1 and this region is region 2. And if we have the D, like in this case this is my D vector in arbitrary direction, like say this is my D2, and suppose this is another D along this direction, say. So this is my D1. So now if I try to find out the components and exploiting the way we did before, I am not going to do the detailed calculation, but you can understand that. So D1 perpendicular minus D2 perpendicular is equal to sigma f. That is the first equation you will have, and for B it is 0. So you should have B1 perpendicular minus B2 perpendicular is equal to 0. So the perpendicular component of the displacement vector is discontinuous. It depends on the surface current density. If there is the surface current density, free surface current density, if there is no free charge here, then it is the perpendicular component is continuous, but if there is, then it should be equivalent to, this difference is in fact equivalent to the free surface charge density. And for magnetic field, B field, this perpendicular component is conserved. Now, the parallel component, whenever we discuss the parallel component, then I need to use the expression of H here, and for parallel, so I am going to use this curl expression, that means this line integral I am going to use. So, in first case, when I use the surface integral, then the equation, this equation and this equation was considered, and that is why D and B components are written here. Now, we are going to consider the other two equations, which is the line integral, and for line integral we need to write down the expression in terms of E, boundary condition in terms of E and H. So, again let me draw quickly the surface. So, this is the surface. So, this is our surface, say, and we have previously we have a surface here, but now we should have a line here, closed line. These things we did in earlier class, and inside below we also have the continuation of this line, and the line direction here is along this, and this length is usually L, and the surface current that is flowing here, free surface current, is Kf, and this is the perpendicular direction of the surface N, and this is region 1 and this is region 2, region 1 and region 2. Now, here if I calculate like the way we calculated earlier, so it should be E parallel 1 minus E parallel 2 is equal to 0, and if you calculate in terms of H, it should be H, okay, it is this, it should be H parallel 1 minus H parallel 2, that should be equivalent to the Kf cross N, because If, the free current, is simply Kf dot N cross L, and that is Kf cross N dot dl. Now, if I exploit this equation and this equation, considering the line integral here, so this is the result one can expect. Okay, this is the result one can expect, and this is precisely the boundary condition in terms of D and H, in terms of D and H. Now, after having these boundary conditions, let us now jot down what we had so far in terms of Maxwell's equation in different medium. So, here what I am writing is the Maxwell's equations, Maxwell's equation in different cases, in different mediums, in different cases. So, the first one is the most simple one that we discussed. So, in first case I write in free space or in vacuum. In free space, what we had, both the source term rho and j should be 0. That makes the equation even simpler, and I simply write this equation in this way. So, equation 1 is divergence of E is 0, equation 2 divergence of B is 0, equation 3 curl of E is minus del B del T, and finally we have curl of B is mu 0 epsilon 0 del E del T. Rho and j is 0. So, this is the expression, these are the expressions in free space. This is Maxwell's equation in free space. Okay, so now the Maxwell's equation with source term. If there is a source term, so how should I write? So, we write Maxwell's equation with source term when we write source term, that means now no longer rho and j are 0, rather they are not 0. And the fourth equation, again a similar kind of equation will be there, only equation 1 and 4 will be modified. So, divergence of E is now rho divided by epsilon naught, then I have divergence of B equal to 0, then we have curl cross E is minus del B del T, and then curl of B is mu 0 j plus mu 0 epsilon 0 del E del T. This is the expression, most of the books you will find. This is the expression for Maxwell's equation with source term, but not in the medium. We need to introduce this rho and j explicitly in a different way in the medium. That I like to write here. So, now if I want to write Maxwell's equation in matter, then the form of the equation is slightly modified, that we discuss, but let me write it here. So, the first equation will be modified like this. Instead of E, I am going to get D, and here I have rho free. Second equation will not going to change because there is no source term, and I mentioned that the term, the Maxwell's equation having the source term is only going to modify when we are discussing the Maxwell's equation in a matter. Third equation again will remain unchanged. So, curl cross E is equal to minus of del V del T, and finally I have the equation again that having certain modifications. It should be JF plus del T of the vector D. Here you should remember few things, because I am writing this in terms of D and H. So the expression of the D and H should be given. The expression of the D is in terms of E, it is epsilon 0 E and the polarization P, that is one. An expression of the H in terms of B and magnetization M is also there. So let me write it minus M. So we can also write few things, because the relationship with D and E and H and B can be written in this way. So here it is epsilon 0 E, and P again I can write in terms of E, like epsilon 0 chi E E. So that makes me epsilon 0 1 plus chi E E, and that is simply D is equal to epsilon E, where epsilon is epsilon 0 1 plus chi E. This is the way we define the relationship between E and D in terms of epsilon, the permittivity. Similar way I can have my B here. So B is simply mu 0 H plus M. So here I write mu 0 H M. There is a relationship between M and H, and okay, I have mu 0 multiplied here, so it should be mu 0 M here, and let us take mu 0 common first, mu 0, then I have H plus, then I have magnetic susceptibility multiplied by H. That is the relationship between M and H. So it should be H here. So I can write it as mu 0 1 plus chi M H, or simply B is equal to mu H, where my mu is equal to mu 0 1 plus this. So this is the way we can represent the Maxwell's equation in different cases. In free space, the first one. Second one is when we have a source term, and then when we have a Maxwell's equation inside a matter. Inside the matter, only thing that you need to consider is now it is written in the first equation and the last equation, that is the equation having the source term is modified. It is written in terms of D, which is the displacement vector, and H, the magnetic field, is now written in terms of H, and the relationship between the B and E with D and H is shown here. So the relationship is this. This is the relationship between D and H, and this is the relationship between mu B and H, D and E, and mu and H. Okay, so now we have an idea that how to write down the Maxwell's equation in different system. So now we will going to discuss about the electromagnetic wave. So our next topic is to understand the EM wave in a conducting medium, in a conducting medium. So far we are dealing with the dielectric medium and write down the Maxwell's equation. Now the situation is different. We are having a conducting medium, dielectric medium or magnetic material. We deal with the Maxwell's equation, but now we are dealing with the conducting medium, and in conducting medium the Maxwell's equation is going to modify so as the corresponding wave equation that we are going to find out, and that should be our final topic in this module. In module 4 we have a final topic. This is the final topic. So eventually this is our last class, but we will going to discuss few tutorial problem later. So so in the conducting medium, so let us write in this way. Let the conducting medium is charge free That means we consider there is no free charge, rho is 0 here, and external current free also. External current free means there is no free current charge density. So, this is F is 0 and also there is no JF, and this is such that the current existing in the medium are produced by the EM wave itself. So, what is the meaning of that? That we are having a medium where the free current charge charge density is not there, and also the external current is free. There is no such external current. Only the current that, because it is a conducting medium, the only current that we have in the system is due to the electromagnetic wave itself. So, what current we are talking about here? We are simply talking about the current that is driven by the external electric field, and I can write an expression like J is equal to then sigma E. So, that is a well known equation. So, that is the relationship with the current that is governed by the electromagnetic wave. The electric field is there. So, J should be sigma E, where sigma is the conductivity. So, the Maxwell's equation now under that condition, the Maxwell's equation we can write in this way. The first equation for this case, the first equation is divergence of E is equal to 0, because there is no charge density. Second equation, divergence of B or divergence of H, let us write in terms of H, is 0. Third equation is curl of E is minus of del B del T, let us write in terms of H. So, I should write it minus of mu del H minus of mu del H del T, and the fourth equation is curl cross H is sigma E, because there is a J and that J should be sigma E, plus epsilon del E del T. So, these are the four equations we are having. Now, if I want to find out the the Maxwell's equation, Maxwell's wave equation, so I should make a curl over the equation, third equation, curl over E, the standard procedure that we followed. That should be equal to minus of mu, then del T, and then I have curl over E, curl over B. No, here I should write curl over H, because I write in terms of H. So, it should be curl over H. So, left hand side, the famous identity, that del square E plus divergence, gradient of the divergence of E. Right hand side, what I write is simply minus of mu del T, then sigma E plus epsilon del E del T, that I find. Now, this is equal to 0, this is equal to 0. So, what I get? We get simply minus of del square E, and then plus of mu epsilon del 2 E del T square, my pen is not working properly now, del T square minus mu sigma, then we have del E del T, that is equal to 0. So, we have a first order derivative term with respect to time, first order derivative of E with respect to time. So, that gives me, so that is the wave equations. Up to these we can identify this to a wave equation, but this additional part is putting some kind of damping. So, this is a damping part. So, this equation is overall a damped wave equation. We are having a damped wave equation here in our hand when we deal with the okay, here I think I have this sign will be plus. So, we have a damped wave equation in our hand, and let us now consider the plane wave solution, because we know the solution for the wave equation is plane wave. So, the plane wave solution, if I consider plane wave solution, that is E is equal to E0 e to the power of I k dot r minus omega t. That is the way we have our plane wave. Now, if I put this plane wave here in this equation, so what we get is like putting the solution into the damped wave equation, then what we have is this. We have minus of k square plus mu epsilon omega square plus mu sigma I omega. Just make the derivative and you will get all these things. Now, k square is simply omega square mu epsilon plus I mu sigma and omega. Now, this is a complex term. You can see that this is a k is now complex, a complex term which is having a term associated with I, which is here sitting. Now, I can write k in two form. So, say k I can write as a real part, k is a propagation constant. So, I can write this propagation constant real part and an imaginary part like this I m, kr plus I k m, I k I m. Now, k square is simply k r square minus k imaginary square plus 2 k r k imaginary, and there should be a I term, or you make a square of that. So, if I tally with this equation, whatever we get here, this one from this one and this one, then I can write it like k r square minus k imaginary square, that is simply omega square and then mu epsilon, that is one term, and another term is 2 of k real k imaginary is omega mu and sigma. So, from that two equations I can have this relationship, and if you solve that, it is not a complicated task to solve it, two equation, two variables, two unknowns. Then one can have k r solving, I am just writing the solving, you have k r is equal to omega root over of epsilon mu divided by 2, and then we have root over of 1 plus sigma mu omega whole square and then plus 1 whole to the power half. That is my real part of the k. And what is the imaginary part of a, considering the damping? Imaginary is equal to omega root over of epsilon mu by 2, then we have root over of 1 plus sigma divided by omega, sorry, this is omega epsilon, not, I am making a mistake here, not mu, it should be epsilon omega epsilon omega square minus 1 whole to the power half. That is the solution for k real and k imaginary. Now, the solution, if I go back to the solution, it was E is equal to E0 vector e to the power of I k dot r minus omega. That is the form of the solution. Now, k is now a quantity which is having the imaginary part. So, I should have write k, say a direction n, and this is having two parts, the amplitude, it is real plus I k imaginary and the vector unit vector n. So, if I put in the solution, one can readily find that E vector is simply E0 e to the power of I k real unit vector n dot r minus omega t, that is a sinusoidal kind of term, but we have an exponential term as well. So, let me erase this part. We have an exponential term which is a decaying part governed by the imaginary part n dot r. So, this term is the attenuation we are having, this is the loss term, this is exponentially decay. So, few things we can note. So, let us note these facts, that when so when sigma is 0, okay, I am making sigma is 0, then k imaginary, whatever we have k imaginary, if I go back to the equation here, if I put sigma equal to 0, then you can see that k imaginary simply vanishes. So, k imaginary is 0, and so there is no attenuation, and this attenuation is coming only because of the non-vanishing sigma. This conductivity basically gives some sort of attenuation here in electromagnetic wave. Now, for a good conductor, we had the condition for a good conductor, what we have is sigma divided by that quantity, sigma divided by omega epsilon should be very greater than 1, and in that case we can have k r is equal to k imaginary, which is nearly equal to omega and then sigma mu divided by 2. So, that we can put this condition, you can put here in the solutions, and if you put this in the solutions, then we simply have k r k I m nearly equal to this. Now, the quantity the quantity 1 divided by km reciprocal kim, that is the reciprocal of the imaginary part of the propagation constant, is generally measures the depth at which the electromagnetic wave entering a conductor is attenuated to 1 by E of its initial amplitude. Its initial amplitude, which is straightforward here. So, Km is here. So, when Kim, if I have 1 by Kim, then this term should be to the power minus 1. So, R is the, if I put this R in such a way that it should be 1 by Ikm, then this quantity which is loss, it should be 1 by E. So, the amplitude will be reduced to 1 by E term. So, that quantity, so whatever the its initial amplitude at the surface. So, whatever the surface we have, so the amplitude is dk 1 by E time. So, it is known as skin depth. So, there is a specific name. So, it is known as skin depth. So, 1 by Km is equal to delta the skin depth and can be defined by 2 divided by omega sigma and mu. So, if you can see that for a given conductor, when omega, the frequency is high, the skin depth is small. So, very high frequencies, suppose we have a conductor here. So, when the electromagnetic wave is propagating in this conductor, suppose this electromagnetic wave is propagating throughout this conductor. So, when it goes inside the conductor, there is attenuation, huge attenuation of the amplitude. So, this is exponential decay. So, when it goes here, its amplitude will decay down. So, this is say 1 by E amplitude, and from here to here the depth we call the skin depth delta. So, now if the frequency is very high, then the skin depth is very small. So, most of the electromagnetic wave for high frequency electromagnetic wave is moving through a conducting material through the surface. So, over the surface so this is the E value that is attenuating with respect to R. So, most of the electromagnetic wave, the entire part of the electromagnetic wave is containing over the surface of the conductor, because if it enters into the conductor, then there should be a decay, and this decay is due to the imaginary part of the propagation constant k, and that is arising due to this quantity, sigma, that is the conductivity. The conductivity of the material in the conductivity of the conductor basically attenuates the electromagnetic wave and restrict the electromagnetic wave to stay mostly in the surface of the conductor. So, with that note, I would like to conclude here in today's class. So, today is essentially the last class of the technical discussion. So, we should have a couple of more classes where we are going to discuss about few problems, tutorial problems mainly, which will be helpful for you, and you can solve a different kind of problems, but these problems in the tutorial will be some typical type of problem typical types of problems which generally you face in the exam. Okay, so with that note, I would like to conclude my discussion here. Thank you very much for your attention, and see you in the next class.